Hello, we're going to talk about period of SHM. So SHM is simple harmonic motion, which is a spring with a mass m, and the spring has a spring constant equal to k, and it's sitting on the floor and it's vibrating back and forth. So we're going to derive this one here, and there's other things that we will be doing too, okay? So the period of this vibration to the left and right, right? So this mass is going to be vibrating left and right. How much time it takes to complete one oscillation, okay? This is period of one oscillation, right? So let's say if you start from let's say if you pull it you push it right to this location and you let go, then it will be coming back and it will continue and come here, then come back here, and then come back, right? So you start from 1, you go to 2, and then you go to 3 with expansion, you come back to equilibrium, you come back to here with the compression. So that's called one cycle. So 1, 2, 3, 2, 1. Okay, so that's equal to the period T. So we are saying that that period is equal to 2 pi times the square root of the mass divided by the K. And we will show you that. Okay, so in order to do that, we are considering UCM motion. Okay, you may be wondering, why are we doing UCM when we are thinking about SHM? The fact is that UCM is relating to SHM. How so? So if you're doing a UCM with a mass and doing this UCM around the circle right now, if you put your eyes in this location and looking this way, and then what you are seeing of this mass motion that doing UCM, this mass would then become like a SHM. Okay, so that's what we're going to show you next. So we're going to call this V, the linear speed, is going to call that Vmax. Okay, so that will be Vmax here too, right? So the Vmax will be here too. So Vmax is constant, is everywhere, right? So the Vmax will be going down this way, which is the VCM's Vmax, right? The linear speed. Now let's look at this theta here. This theta here is between this A, usually it's the radius, but radius here we're going to call that A, okay? So we're going to call this one here A, right? This is the radius, right there, right? So that's the same as that, the radius of the circle, which is the A. The reason it's called A because it's the amplitude, right? Amplitude, which is the maximum displacement. This is equal to the maximum displacement. And displacement here means the X, right? So the X is changing when you're doing the SHM, left and right, right? So if you're going from here to here, this is your X right there. And if you go to the maximum, then this become your A, right? This is your A, and this side also A. Okay, so now this is theta, and this is 90 degrees right there. And this one is 90 degrees to this one here. So then this one here would also be theta, okay? This one here, this angle will be theta, just like this one here. So now we're looking at the congruence of these two triangles. So we're going to call this one here, let's say this triangle here and this triangle there, right? This congruence. So when you look at that, you're going to see the V, which is this one here. V is this one, okay? And basically it's the velocity of this SHM that's going this way right now. This is your V, okay? So this V compared to Vmax, okay? V compared to Vmax. So this edge compared to this edge. So this V is facing theta. So facing theta is this one here. So it'll be square root, and this is 90 degrees. So A squared minus X squared, right? This is A squared right here, and this is X. So that's A squared minus X. So this one here over A, right? A is right here, facing the 90 degrees. So facing 90 degrees is the Vmax. So that's valid, okay? So why are we doing that? Because in the conservation of mechanical energy for the SHM situation, we have, this is the kinetic energy, and this is the potential energy, spring potential energy, and that's equal to the total energy when you are at the maximum displacement, which is A, They are equal. And if you rearrange this equation and solving for the V, you find that that's equal to this, okay? You just to go through algebra, you find that V squared is equal to V max squared, and A squared minus X squared divided by A squared. And that indeed is the same as this equation here. So you can see this geometry here through the UCM and SHM relationship is telling you it also can be derived from the conservation of mechanical energy for the SHM case. All right, so you can see the relationship in this fashion. Now we're going to go straight into the derivation of the period now. So we know the Vmax is equal to 2 pi A, which is 2 pi R, right? 2 pi R, so this linear speed is equal to circumference, and this circumference is 2 pi R, and R is the A, right? So 2 pi A, so this is circumference, right? Circumference, all right? And 圆周, right? This is 圆周, right? Okay, in Chinese. So 2 pi A divided by T. So distance divided by time is your velocity, your constant linear speed here, okay? And then you rearrange it so then T goes here, Vmax goes here, so T is equal to that. Now, again, we apply conservation of mechanical energy for SHM, which tells us the maximum kinetic energy, which is the total energy of SHM, it's equal to maximum potential energy of the spring, which is the total energy of the SHM. The two are equal, and then you're solving for the Vmax, so you move the m over and 1/2, cancel, right? This cancel here. Then you see the Vmax is equal to square root k divided by m when you divide over, and then a comes out from the square root. So then you're going to put this one here using this equation right there that we just had right there, okay? So this one here, we're going to put this one here into here. Vmax equal to this into here, and you will see A will cancel out, right? This one puts in there, A cancel out, and this one flip, M will be coming from the top, K will be at the bottom, and you still have the 2 pi. So then that's your equation right there, the 2 pi times square root M divided by K, which is the period of SHM. And you can see they are all coming from the conservation of mechanical energy for SHM, okay? But you can also get it from using this UCM SHM relationship through this velocity equal to distance divided by time, and you're looking at what Vmax is, and you will see this T that you find from the UCM is the same T that you find in the SHM. So the T in the UCM when you go around once is T, okay? But then when you have this oscillation from here to here, right? So 1 to 2, and then to 3, back to 2, back to 1, that's also T. So the T for SHM here is the same as the T for the UCM here. All right, so that's what we have, and thank you for watching, and until next time, bye-bye now.